Bom, então vou apresentar hoje o professor Frederic NALLET. Ele está aqui por 3 semanas, essa é a segunda semana dele, dentro do quadro de cooperação capsótica. E ele é uma pessoa que já está há muito tempo trabalhando nessa área de cristais líquidos, de fluidos complexos e fluidos em geral. E além de ser um professor da Universidade de Bordeaux, ele é um pesquisador do CNRS, que está ligado ao laboratório CNPq, onde a gente tem um convênio. E ele tem uma experiência muito grande, não só experimental, com várias técnicas experimentais, espalhamento de luz, espalhamento de nêutrons, espalhamento de raio-x, mas também é um cara que sabe fazer teoria, que sabe fazer modelos e é muito didático para escrever. Eu espero que todo mundo possa aproveitar um pouco essa oportunidade de ele falando. E depois as pessoas que quiserem conversar com ele, que ficar na minha sala, o Cristiano na sala, o Caminho, então está à disposição. Se vocês quiserem discutir com ele, só ligar e combinar.
Okay, so I'm sorry, my Portuguese is not, well, it's very limited in fact. So I could do it in French, but it's not appropriate in international scientific relations, so it will be in English. Well, I'm of course very happy to be here and quite, in fact this is my third trip already to Brazil, and because of that scientific cooperation with the beach. Well, I will talk about what I'm doing for a very long time already in Bordeaux University and Bordeaux University, and this is the laboratory itself, the Centre Jean-Paul Pascal, mainly studying well, colloidal dispersed systems with the help of scattering techniques. In this particular case, the focus will be small angle scattering and more specifically even about X-ray scattering. So, well, colloidal systems are the main interest for me, part of complex fluid systems. And in this talk I will just first describe the motivation and some background about soft matter and small angle techniques. So this will be the first part. In the second part, I will emphasize about the specific aspects of soft matter when studied with small angle scattering techniques. My point of view being that the central aspect, the main properties, being that the structures are not very well ordered. Because mainly of the finite size of the systems, because soft matter is soft and it's easily disordered, so the orientations of the components are most often random. And since soft matter is soft, it is also quite a lot submitted to thermal fluctuations, and they have also a very important role in the way we can extract informations using X-ray scattering for studying colloidal systems. And the third part will be just illustrating the aspects of this talk by selected examples coming from many years. Well, so soft matter, why precisely soft? Because the systems we are interested in are usually characterized by very large-scale structures. In the true colloidal system, the scales can be, in fact, almost macroscopic. And this is, for instance, the colloidal needle that is studied in our laboratory by my colleagues. I'm more interested in still large-scale system, but smaller scale than that. In the case of self-assembled objects, and let's say an obvious representative of that is the here schematically drawn the surfactant bilayer. So this dimension is still about the molecular molecular scale, but that dimension is usually very large. So we know that bilayer can make vesicles, for instance, or stack in laminar phases and various kinds of structures. In any case, there are large scales in the problem. And because of these large scales present in colloidal dispersed systems, at the same time the interactions between objects are quite weak and most often also anisotropic. And these weak interactions give rise to various kinds of orders, not very good ordered systems usually. So it's on occasion orientational order only. So we have the liquid crystals with orientational order like nematic or cholesteric systems. In case where it is slightly more ordered but still not completely 3D ordered, we may have symmetric or columnar phases depending on whether the order is one-dimensional or two-dimensional. Well, in some other occasion, we can have true crystals in the sense of crystallography, 3D objects, of course, at a very large scale. And because the scales are large, the interactions are weak and the objects are weakly bound. Now, combining that property with weakly bound objects with the fact that thermal fluctuations are always present at room temperature, fluctuations, thermally induced fluctuations may be quite large. And from the point of view of scattering studies, the picture is that in a scattering experiment, you record at the same time a significant drag scattering, so localized peaks that are related to order, whatever order be present in the system, and also a lot of diffuse scattering that is related to well, disorder or poor order in the system. So the drag peaks are well defined, but at the same time you have in between drag peaks and in other direction in reciprocal space a lot of scattering. And the problem in studying colloidal shapes and stacking order in soft matter is precisely to, let's say, trying to extract what is related to order, drag scattering, and separate from that what is related to objects, the shapes, and this is diffuse scattering. Well, let me try to explain how it works in more details. Going back shortly to small angle scattering, well, typically we are using incident radiation, and it will be, in our case, mainly X-rays, irradiated onto the sample because the sample is not homogeneous material, it scatters radiation in all directions, and we observe at a certain scattering angle. And we are concerned with small angle scattering because scale being large, the typical size defined by that wave vector has to be comparable to the reciprocal of the scale, and with the numbers that are appropriate for soft matter, the angles are either extremely small for very large scale structure, or let's say up to typically 20 degrees. This limit being not very sharply defined, of course, but well, it means that the molecular details are not really cropped yet. So small angles mean you are really studying what occurs at small angles in this case. More technically, you know that the scattering experiment is a measure of average properties, average in space and time, over, in fact, a macroscopic irradiated volume. So we are not concerned with individual particle properties, but really what is measured is related to collective properties of many, many different objects. And since the scattering experiment is related to Fourier transform, the typical scale, as was said previously, is related to the size proved by this scattering wave vector here. And what is really measured is this Fourier transform of scattering length, density, or heterogeneities. Now, depending on radiation that you use, maybe light or neutrons in some cases, and here I will mainly concentrate upon X-rays. The formalism is the same, whatever the radiation, but what are really heterogeneities specific, and in our case it will be mainly the electron density, the local electron density in the system. So with a prefactor for consistency of the units. Okay, so in the case of small number scattering, we are not yet probing molecular details. We are studying things at a rather large scale. And this implies that we can use a continuous description of both the solvent medium and the dispersed object, colloidal object, or self-assembled particles. And this is quite different from the solid-state crystallography, for instance, where the description is really rather point-like. Here we use a continuous description of the properties of the system. And moreover, at least within the compressivity approximation that holds quite well at small angles, continuous media can also be treated as homogeneous domains. Of course, there are homogeneous solvent domains and homogeneous particle domains, meaning that at the scale you are interested in, we can model the scattering lengths, densities, heterogeneities, like a continuous thing within solvent domain, for instance, and discontinuously moving to another continuous constant value within the particles. So this picture is some kind of arbitrary fluctuations in, let's say, scattering length density within the dispersed system. It is probably along that line, and locally along that line you see a solvent domain, for instance, and the particle domain here with a discontinuity between the two domains. Of course, if you go to more local scales, molecular details are becoming important, and in some cases it's better to use a less discontinuous description for analyzing the data. But for a first approach, this is quite useful. So this leads to a very common and very useful description in the dispersed system, which is based on geometrical concepts. So we have domain of solvents, and dispersed in this solvent some particles or objects or whatever colloids you are interested in. And along this line, for instance, if you are in the solvent, the contrast level is, for instance, 0. And if you are within a given colloidal particle, the pink one, you have a given value, a given constant value for the contrast, which will be different if you are going inside the second type of particles, and so on. So this is the main idea of the description. Discontinuous step at the boundary of objects. So of course, for this to be working, you have to know where are the objects located, what object at what time. And it is convenient and quite usual to separate center of mass coordinates for the objects from local coordinates within objects. And the general expression for the intensity, scalar intensity at small angles, then becomes something like that. We are summing over all the colloids. So we are within the first one, for instance, we have this 0 here. considering the center of mass position of the first coloid, and we repeat that everywhere in the irradiated volume. And that part of the signal is what is usually referred to as the form factor of the coloids, and the information about colloidal shapes and principle contained in that integral. And this part is usually called structure factor, and it contains information about the stacking order of the colloid, the way the different colloids are stacked in space. Okay, in slightly more details, the form factor is precisely defined by that integral related to the previous one shown to you, with average over orientation, because that object is rotating space around its center of mass, and also deformation, because colloidal objects are not always rigid objects, and they change shape because of thermal fluctuation. Well, in fact, this is the formal definition for the case of disordered systems in diode limits, and I will give an extension of that in the case of more ordered soft matter system. And well, here it's normalized to 1 at 0 angle by the colloidal volume normalization. The other part, the structure factor.
Where do you put the time dependence on the form factor?
There is no time dependence. So the question is why I've not included the time dependence. Well, because of that average. The average coming from, well, formally the general expression. Let's take more here. So colloids are moving and changing shape because of thermal fluctuations. But what is recorded on the detector is the kind of average over these, let's say, thermal fluctuations. So the in what is called static scattering, the speckle information is lost. Not just interested in average value of the scattering of the scattered signal.
Because when you consider, for example, time fluctuations of an object like this, if you leave this for a long enough time, it can be approached by a sphere, for example.
Well, that's a complicated question, in fact, because it may depend on whether that colloidal object is, let's say, in a rather dilute and disordered system, or a component of a more ordered object. So in the case where it is fairly dilute, of course, because of the, let's say, for instance, a small rod in that very dilute solution, the orientational average that is contained here, well, not here, form factor expression, the time dependence will be lost. But still, the mathematical function will be different in the case of a spherical object fluctuating and rotating, that changes nothing, and the slender rod fluctuating, the function are different. The dependence will not be the same. So the shape is contained, the influence of the shape is contained in the thermal average, but even if the result is not time dependent. I'm not sure I can explain it here. I discuss more details perhaps. Thank you. Okay, so this was form factor, and well, in principle, you may have the same question for the structure factor, or technically that average or over instantaneous. Again, this is time dependent locally. Special locations of colloidal pairs. And since everything is moving constantly because of the thermal Brownian motion, that quantity is fluctuating a lot. But it becomes time independent once thermal average is performed. Okay, again, for technical reason, I'm normalizing here by the number of colloidal objects present within the irradiated volume, meaning that the limiting value at very large angle, considering the problem that I'm talking about, that is small angle. So at large small angle, if I may say, the form factor is supposed to reach some value 1 because of that normalization. Okay, I will be more interested in dense and or ordered structures in colloidal matter, where these objects will be stacked in some ordered way, not completely at random. And this very general expression, if you expand it, truly speaking, this is that Colloidal thing, which is quite complex because in dense and ordered structure, the center of mass degrees of freedom are also coupled to orientational and shape degrees of freedom. So that average that you have to perform should be performed at the same time to the coupled center of mass variables and local colloidal variables. Well, so this is essentially impossible, well, in my opinion. So I would welcome any suggestion for treating that rigorously in the most general case. So there are two escapes. One escape is to dilute the system, and then in dilute system there is no longer any correlations between center of mass, and that structure factor part can be neglected. And of course this approach is very common and very useful. I will not talk about that. The second approach, which may not work in all cases, would work in the case of some special cases, but fortunately enough quite common in the field of soft matter studies, where the colloidal objects are in a sense well calibrated. So what does it mean? It means that the objects have no, or perhaps very little, so you can safely neglect that, shape or orientational fluctuations. So you have, let's say, rigid objects that are well confined in space. So this occurs obviously in the case of spheres, because the sphere rotates, it is always a sphere, so the shape is not changing, whatever the orientation. But it is also the case in the case when the building blocks of the systems you are studying are well stacked. So for instance, this is a schematic drawing for platelets being stacked like bilayers in a laminar phase, for instance, or cylinders here being stacked in a 2D hexagonal phase. So because of the stacking order, you may at least hope, in some occasions, this turns out to be true, you may hope that the shape of individual object is not fluctuating too much. So it's quite significant to at least approximately declare that one platelet has a given shape and at the same time a given orientation, because it is stacked within this laminar structure over all the time. So if you come back to this expression, the local properties are no longer fluctuating. So this average here can be moved to that part. Of course, this is an approximation and it may not work in all cases. In particular, a very important case where you cannot use that kind of description is the case of nematic or cholesteric phase, because you still have orientational fluctuations of, let's say, rot in the cholesteric phase of DNA, for instance. So the objects in that case are not well calibrated. And at the same time, in the cholesteric phase of DNA, for instance, objects are fluctuating as far as their orientation is concerned, but at the same time they are fluctuating as far as their center of mass are concerned. So I will restrict to those special cases, but still not very special, for the discussion is quite general indeed. And in that case, the spectral intensity becomes, well, less discouraging. So the most simple case, of course, is the case of spheres, because in the disordered sphere of in the disordered phase of identical spheres, there is no reason to perform any kind of orientation on average, and they separate readily the form factor contribution from the structural factor contribution, with here the normalizing factors that comes from the way of defining things. Okay, slightly more complicated is the case of still spheres. So there is no information related to orientation of the local object, because the sphere is the sphere in every orientation. But in the case of the 3D ordered structure, and now there is a vector on the wave vector, because this the structural factor will depend on the orientation of the crystal with respect to the scattering axis of the experiment. And the most complicated case will be the case of the lateral phase of the 2D columnar phase, where the objects are anisotropic, so there is vector dependence on the form factor, and the stacking is also anisotropic. There is also a vector dependence on the structural factor. But still, you can have two separate factors because, well, I am within this description of evaluated objects. So there is no orientational fluctuations for the objects themselves, and that makes the separate contribution here. And the center of mass fluctuations that are, of course, anisotropic in the laminar phase as well as in the columnar phase. These center of mass fluctuations are not coupled to shape fluctuations. Okay, so this is a quite standard case of disordered structure of, let's say, identical spheres. I will not consider it, and I will focus in more details on those two kinds of well-calibrated systems. Okay, now the point is that all these colloidal systems we are interested in are ill-ordered in some sense because of quite different reasons that I've mentioned in the beginning. So the first one is related to the kind of finite size effect. Since the structures are large, in the irradiated volume, you have not so many correlated objects as measured by the resolution of the scattering experiment. So if you are doing X-ray scattering on silicon or diamond, for instance, you have many carbon or silicon atoms correlated in the crystal. But in the case of soft matter, where the distance is much larger, the repeat distance between objects is much larger, the number of correlated objects as measured by the incident radiation is much smaller. And in the case of randomly oriented domains within the radiated volume, there is a very old and classical Debye formula for the structural factor related to the number of reticular planes that you can identify within the scattering volume. For a soft matter ordered system with a typical scale related to the first order Bragg peak location, for instance, that is written here as Q0, measured at the scale of the resolution of the experiment, it turns out that in soft matter the number of reticular planes is usually quite low. So it's not 10,000, it's perhaps 100 or less than that. And because the number is small, there is not an infinite number of Bragg peaks as in classical crystallography, but only a small, a limited number of them. And again, in classical crystallography, the height of the Bragg peak is infinite and becomes finite if you take into account the finite resolution, of course. But with a small number of reticular planes, the height of a Bragg peak is quite low. Okay, so if the Bragg peaks are not enormously strong with respect to other contribution to the scattering intensity, it means that you can see, and this is precisely the experimental observation, you can see Bragg peaks at the same time with diffuse scattering, which of course also occurs in usual crystallography. But in the case of usual crystallography, you have to have a very sensitive experiment to measure the diffuse scattering because the Bragg scattering is so intense. With soft matter, this is not the case. And it turns out that it will be an advantage. So, for instance, here I have been considering a small crystal with a body-centered cubic symmetry, and it's quite easy with a modern computer to have the simulated randomly averaged structure factor for a finite size. So the finite size is you take 3 by 3 by 3 or 6 by 6 by 6 such cubes, and you compute the average of the structure factor, and you see that the Bragg peaks, they are present, but they are not very intense. So the infinite limit for the structural factor is 1, and even in that case where you still have 200 and something objects, the height here is only 4, so it's not enormously strong. And of course, the first order Bragg peak is even less intense with a smaller system. So the orientational average of the structure factor remains always close to 1 because of those finite size effects. And the Bragg peak, well, they are not that significant. Weak Bragg peaks, meaning that the diffuse, or related to shape of the curve, the diffuse scattering will be more easily observed. And the same reasoning is true also in the case of 1D or 2D ordering. If you consider the appropriate average of the structure factor for 1D or 2D ordering. So a second, also quite important effect in soft matter is the presence of thermal fluctuations. So thermal fluctuations, they are always there, and they have been well described in crystallography by Debye and Waller long ago. So basically, the idea is that the center of mass of the scattering objects, and in our case these are colloids, they are well defined at some crystallographic position plus some thermal disorder. Meaning that the sum that you have to make to compute the structural factor is damped by those thermal disorder terms. And because the interactions between colloidal objects are weak, as mentioned in the beginning, the thermal disorder is usually quite strong. So the damping of the bright peaks is also quite strong in soft matter, with the same consequence as finite size. So you have weaker bright peaks, especially at higher order, because that thermal damping increases with the magnitude of the scattering wave vector. And in between bright peaks, so you have a lot of thermal diffuse scattering. And there are even some special cases in soft matter where the fluctuations are not even large. They are giant in the sense that there are some divergence. And this is in particular true for the elastic distortions in nematics or smectic liquid crystals. Because of the particular structure of the orientational order in the nematic system and the orientational coupled to translational order in smectics, there are diverging fluctuations in the long wavelength limit. And this is, of course, well known in the case of nematic system. It gives rise to light scattering, to the phenomenon of nematic opalescence. It's also quite important in the case of one-dimensionally ordered liquid crystals, and is known as the Landau-Pyrus instability that results from the diverging correlation function coming from giant elastic fluctuations in such systems. So in particular, in the case of smectics, or 1D ordered liquid crystals, 1D ordered in 3D space, the translational order is lost. So this is what is known as Landau-Pyrus instability. There is no real 1D order in such a system because of the logarithmically diverging elastic distortion. And the consequence of this is a very strong thermal diffuse scattering, which is even more intense than the Debye-Waller usual thermal diffuse scattering. The bright peaks are damped, and that was also the case with Debye-Waller damping, but at the same time broadening. So there is an intrinsic broadening that comes from thermal fluctuation. And so the effect is huge, and it is here represented on this drawing. So in the case of very high rigidity, there is no broadening apart from the finite resolution of the system, and all the bright peaks have the same height. But as soon as you introduce some flexibility in the lamellar stack, you very quickly lose the bright peaks, and with orders of magnitude for the elastic constant in smectic lamellar phases, you may just see the first, as in this example here, first, second, and third order peak, and that's all. This is quite common, and this is a special consequence of those giant smectic fluctuations. So now you have I think the broad framework, and I'm now coming to some examples. So the first example will be devoted to a soft matter system, which is a block copolymer microemulsion. So we have two organic solvents that are non-miscible, and each solvent is selective for one block of the block copolymer. And because of that particular chemical structure, you may expect long-range order, either 1D, 2D, or 3D ordered phases. And the very schematic picture of what could be the order in such system is the domain of one solvent covered by the block copolymer molecules and separated from the other immiscible solvent. So this is a kind of surfactant-based microemulsion, but with the block copolymer used as the surface active molecule. Because this is polymer, that size is quite large. And now playing with the amount of solvents, that stacking dimension can also be quite large. So we have copolymer-covered interfaces, solvent domains, what I've called these minority solvent domains, with a given characteristic size and some stacking order. So we would like to know for such system what are the parameters, the sizes and the stacking parameters, what is the real nature of the order. And of course you can do small angle scattering experiments, but because of the strong fluctuations and because also of the finite size effects, you have not so many bright peaks. And well, for the most typical examples, you have only 3 or here only 2 bright peaks. And this is not quite enough to clearly identify the stacking order. So okay, this could be compatible with the 3D body-centered cubic ordering. This one could be compatible with 2D ordering of tubes that we don't really know. So there is some remaining ambiguity. So this is the drawback of soft matter. There are not so many Bragg lines, so the identification of the stacking order is not that easy. You see also at the same time that the scattering intensity displays not only Bragg peaks but also a very intense and strong diffuse scattering. So if you go to higher resolution, and it turns out that this experiment has been done almost here. So I've been collaborating on the problem, but at that time I was not yet in Brazil, but I got the data. So you see the same typical feature that you have at the same time localized Bragg features, so related to stacking order, and at the same time very strong, very intense diffuse scattering, and perhaps you can see here a very nice ring of diffuse scattering. But still, if you do the azimuthal averaging of that image, you see very clearly first, second, and third order Bragg peak, as in the low resolution experiment. You see very nice diffuse scattering feature, and perhaps you want to see here, well, I mean, not this slide, here. Perhaps you want to see the 7th order of the BCC stacking, body-centered cubic stacking of those. Then minority solvent domains are presumably sphere, and the outside solvent is a continuous medium, and the interface are covered by the block coupling. But are we really sure of that? And the idea is then to take advantage of what was previously a drawback, that there are not so many Bragg peaks in the spectrum. So we take advantage of the fact that the structure factor is very close to 1. So all that part here, from here short to perhaps somewhere here, all that part of the spectrum is dominated by form factor features. Okay, in that particular case, we don't know the shape of the objects, but we guess that they might be spheres, and we feed that part of the data to sphere form factors. Having doing that, we can now go back to the intensity, divide it by the form factor that you know, because it has been fitted from the data, and what you recover is the structure factor of the stacking. And so the black dots are the data, and the continuous line here is the simulation that I have shown to you before in the 6 by 6 by 6 cubic domains. And Okay, the agreement is not perfect, but now I think you are convinced that there is really a seventh order in this scalar intensity. And okay, the second order was not very intense, and it's not very intense here, and it's not very intense either in the simulation. So the second order of the BCC cubic system is always of low intensity because of finite size effects. And the same property is also true for that, which is 2, 3, 4, 5. The sixth order, it's visible here. It's not very intense here, but they are a kind of qualitative agreement. So using that description of the scalar intensity, we concluded that the stacking order is really BCC, and we know also the size of the assumed spherical shape from the form factor feature that are here. Well, the time is running, so I should perhaps have more acceleration here. So this is again a work related with the block copolymer but in quite a different situation. So in that particular case, the block copolymer is amphiphilic, so that block will like to be in the presence of water, and that block is extremely or rather hydrophobic, so they will separate from water. The previous system that was a small amount of copolymer and a large amount of solvent. Here this is the reverse limit. Essentially block copolymer plus perhaps a small amount of solvent, and solvent in that case will be water. So depending on the composition ratio, so the size of that block compared to the size of that block, and depending on the hydrogen state, so the slight amount of water present in the system, many different classical structures are expected. These order 3 cubic to the hexagonal or 1 d lateral phase. And of course, if you have those samples and very nice inline and French or international samples generated in France in Grenoble, you can see that you have very nice Bragg lines. And in this case, you see on this line here, characteristic of the BCC structure, and there is no problem in identifying the stacking order in that particular composition, or for another composition you have very nice lamellar order revealed by this equally spaced line. At the same time, what you see is the diffuse scattering is extremely intense for those systems. Perhaps you cannot see it very clearly, but the intensity has been normalized by Q to the 4 here, just to enhance the large angle part of the spectrum. And this here is a form factor feature, in fact, that part below, in a sense, the Bragg lines are form factor features. And here again, the form factor features below the Bragg lines of the stacking order. Well, in other part of the phase diagram for this system, the spectra are unfortunately not that characteristic. So initially dry system has that particular spectrum, for instance, and you hydrate it and slowly it will swell. The hydrophobic domain will separate more, and the hydrophobic size will increase because water will be absorbed, and the spectrum changes to that part. But okay, what is the structure here? What is the structure there? You don't know really. In some cases, you see from the kinetic study that there are schooling-induced structural transitions. So the first one is not very characteristic, but the last one here is in fact the lamellar spectrum. So we would like to know what occurs in such system around the swelling and performing kinetic studies. Again, making use of the fact that diffuse scattering is quite strong, and the large angle parts of the data have been fitted through elementary and for that particular system, well, we use very simple models with the square well profiles. So spheres are used here. Elongated cylinders are used in the case of the hexagon structure, and flat, very flat cylinders or planes are used here. Okay, so it's not easy to see, but the large angle part of these spectra is appropriately described by these form factors. So we know the sizes, spherical radius, cylindrical radius, or thickness of the bilayer from the diffuse part of the cell. Then,
This one here, lateral phase, corresponds to flat cylinders.
Yeah, flat cylinders. So this is a flat cylinder. Yeah. A coin, a very flat object, and now in the laminar phase, those flat cylinders are stacked. Symmetry axis, and well, the drawing is not very good, I'm sorry for that. Stacking flat.
That's the dimension.
So that dimension is well described as very large, infinite in this description. So we are not able to know the size, the lateral size of the bilayers. So that's why, in fact, only one parameter, one size parameter, which is the thickness of the bilayer. The extension, the lateral extension, is considered to be infinite. In fact, it will change the prefactor here, but this would require fitting the data at very small angles, and in that part of the spectrum, the structural factor is also important.
So you may see the difference from the experimental point of view from this cylinders and flat planes, lamella, or not?
No, this is the same. Since we don't know that size, it's not included.
So you could say lamella.
Lamella, yes.
No cylinder, only lamella.
Yeah. Well, since we are describing the large angle part of the spectrum, this is not really significant. For instance, if you are studying vesicles, they are made by layers. There are large structures, spherical shells, for instance. So this is a simple representation. But locally, this looks like a flat cylinder. And in fact, the small angle spectrum of vesicles is very well. The X-ray small angle scattering spectrum of vesicle is very well described in terms of randomly oriented flat objects.
Flat cylinder.
There is no difference. Yeah, precisely, there is no difference. At the scale of X-ray spectrum, there is no difference. There would be a difference if you were to describe the very low angle parts of the form factor. Then you will reach the limiting Linear range. And within Linear range, you have access to this size. So in the case of a vesicle, the Linear domain gives a measurement of the overall size of the bilayer, of the vesicle, excuse me. In the case of this description, it will give the shape, the size of the flat cylinders. There's also a UV limit for flat cylinder. That can be seen, for instance, with clay particles. Okay, so this is a singularity that's very small and related to n very large scale effects and are not considered. So now in these kinetic studies, well, basically there are three different kind of behavior. Either a very simple swelling evolution where there are no phase transition at all. And then for instance, in that particular case, you have access to the size, to the radius of the sphere, and at the same time to the first order radial position, and both are plotted here, so the hydrophilic force are swelling this time, and at the same time the stacking dimension is increasing, so the wave vector location is increasing in time. So there are strange small time behavior, but in the long time unit, there are typically exponential growth of the objects, and exponential growth of the structure. And this is very, very slow, and this is related to the fact that for this to occur, you have to move in the system block copolymer chains, and of course, since it is a concentrated polymeric medium, it takes a lot of time. So this case is not really very interesting. More interesting in the case where you have this swelling in this phase transition, shown those spectra previously, and in fact the first part of the kinetics series is related to you can measure the cylindrical radius. At the same time, you have access to the position of the magnet, and this particular combination is a measurement of the water content in the system, and this is the initial swelling within the hexagonal phase. And in the long time unit, that's spectrum can be fitted as lamellar phase system. With of course, for instance, region and intermediate time. And again, with the long time unit relaxation is exponential with about the same characteristics. Perhaps now the most interesting result of that particular study is the fact that we have been able to reveal a hidden phase transition. Even in the sense that since the starting and final spectra are not very characteristic, you cannot really prove from those two spectra that the first one is BCC and the last one is FCC, face-centered fluid. And in fact, it comes again from the same general analysis where you couple structure factor description with form factor description. And the form factor description gives access to the size of the colloidal spheres, and from the right position you have in fact the measurement of the volume fraction of the water or hydrated lumen. And it turns out that for the two different structural models, the mathematical relation is not the same. And the only way to have a continuous evolution in time is to assume that you start with the BCC model here, you have a phase coexistence region, and you end up with the FCC model with the long time unit. If you don't make that assumption, let's say you start with the BCC model at initial time, then you have a very strange variation of the sizes that cannot be explained because you have steps and you assume no phase transition. So we can conciliate the two aspects by assuming here that the BCC from to FCC phase transition.
In this region, you have really two spectra where you can verify the phase resistance.
I think so because I see not very clearly. I see the points. So I've not shown here the intermediate data. Probably they are can be found in that already quite old portfolios. So this is the Bolton fraction of the hydrophilic domains. So the core at first it's completely dry. There is only the block copolymer without water. The hydrophilic part of the block copolymer without water. And as time proceeds, there is water coming inside, and that domain increases in size. And so this increases in size, and at the same time, this moves towards small angles because the structure is swollen. And the combination of the two, the decrease in this occurs at less speed than the increase of that. So the overall feature is that the amount of water is increasing in the system. But this increasing not enormously. This is 16% of hydrophilic plus water, and it ends up at 30% of hydrophilic plus water. Meaning that you have about 15% of water volume that has pumped into the system. But again, the characteristic time is again about the same as before. So the motion of those block copolymer chains from one micellar object to the next within the hydrophobic matrix that takes a long time. So that information coming all the time, plus this very nice, in my opinion, to answer to sensitive to it, apparition of that structural transition that is not really clearly revealed by the raw data. It requires that kind of data analysis. So probably it seems it's already quite late. I will speak the last part to the conclusion. That is the small understanding techniques are quite often, well at least in the cases I consider, of course, appropriate for the determination of colloidal shapes, and these are basically wedges or spheres or cylinders or thickness of bilayers, so they are not very fancy shapes, of course. Stacking order, and this is already more powerful because I hope that you have been not really convinced, but something close to that you can such method reveal BCC order, for instance, or evidence BCC to FCC phase transition in other structureless features, and in some specific cases related to the part that has been skipped, you can also have access to interactions between the colloidal objects, just by the precise description of the small industrial data. So that particular curve comes from the PhD work made by Everson, Rodrigo, etc. Silva, who know quite well. So he's at present time in Bordeaux, and he will come back in November, quite soon here, for the end of his physics. He's precisely working on that kind of description of the small industrial data. So this is appropriate for dense and other soft matter systems. So in a kind of paradoxical way, in spite of, but at the same time as well as owing to the low quality level of the order present in soft matter systems. So finite size, lot of fluctuations, not so many brightness. It turns out that it can be made advantageous for studying at least some of the many soft matter systems that can be witnessed. Okay, thank you for your attention.
In case of the GFCc, GFCc standardization, could you find the partial volume fractions of each one of the filters?
Well, to really give the correct answer, I have to go back to the lecture. But there is here in red blur the red points that are related to ECC, and here the blue points related to FCC. So probably you are also using a kind of binomial description, the amount of ECC with respect to the amount of FCC. But I'm sorry, I don't remember right now which case. There is a coexistence, yes.
So it should be a first order.
First order, yeah.
And the first order we can see by examining the symmetry. I don't remember exactly. FCC and GCC, the transition between them should be first order. Take into account the symmetry.
Indeed, there is a region of phase coexistence. So if you have two different phases present at the same time in the sample, it means that you have phase, let's say, separation. So this is first order. Well, this is a kind of liquid gas coexistence. This is typical for solid flash.
But it's not which is the order for
Well, you could use not the density, but the volume fraction. Well, it would be the same for binary system. The volume fraction of FCC phase, for instance. So the volume fraction will be 0, 0, 0, 0, and it will jump to a finite value here. No, not it will be 0, 0, 0, and it will increase near to 1 at the end of the phase coexistence region, and then it will be 1, 1, 1, 1. So that can be used as a kind of order parameter. Well, in a rather rough sense. So if you're considering there are probably better definitions for other parameters in structural transformation, but not specialists that I prefer